Lesson 50, geometric mean. Okay, if you write a proportion, a over x equals x over b, and then you multiply, do the cross products, you're going to get x squared equals a times b, and x will be plus or minus square root of ab. So this is called the geometric mean, is a positive of these. So the geometric mean is just the positive square root of the product of two numbers. So if you take two numbers, multiply them together, take the square root, that's called the geometric mean. So, for example, the geometric mean of 4 and 16 is a square root of 4 times 16, or 8. Another example, geometric mean of 5 and 11 is root 55.
Wait, did you subtract 4 and 16?
That's the times.
So she like took the square root of both numbers.
I did. Well, actually, I didn't. I just know that 4 times 16 is 64 because I haven't memorized. Okay, so there is a theorem that has to do with, that you can use the geometric mean with. So we're going to draw a right triangle that is sitting on its hypotenuse. And the triangle is x, y, z. Angle y is your right angle. And then we're going to draw a altitude from angle y and call that point W. And here's the theorem. If the altitude is drawn to the hypotenuse of a right triangle, so in other words, from the right angle to the hypotenuse, then the two triangles formed are similar to each other and to the original triangle. So all three triangles will be similar. Okay, so we have triangle XYZ will be similar to triangle XWY will be similar to triangle YWZ. And I did write those all in the right order. I did along the shorter side to the right angle and then to the along the long leg. I wrote out the theorem, but are you guys okay if we don't write it out in our notes? I don't know. Yeah, Abby?
So if you split it from the right angle again, the opposite, would those be similar to this?
Yes, by the transitive property, because let's say you drew this altitude. Those two little triangles are going to be similar to this one, and this one is similar to those other two. So yeah.
So you have like 5 similar triangles?
You would have 1, 2, 3, 4, 5, yeah. Yeah. So there's a corollary. Have we talked about what a corollary is?
So
I feel like I've heard the word before.
I feel like we have. It's just a corollary is a statement that follows from the theorem. So because the theorem is true, now you can say something else. For instance, you know that if similar triangles are similar, then their sides will be proportional. So that's what the corollary is. So there's a corollary to this theorem that says if the altitude is drawn to the hypotenuse of a right triangle, then the length, oh no, this is the one we want. Oh. Then the length of the altitude is the geometric mean between the segments of the hypotenuse. So if we take these two lengths, multiply them, take the square root, because that's geometric mean, that will be the length of this one. And I'll teach you why. Because they're similar and the sides are proportional. So if the altitude is drawn to the hypotenuse of a right triangle, then the length of the altitude is the geometric mean between the segments of the hypotenuse. So I'm going to show the example using this figure and why it works. If you were to write the proportion between these two triangles, and you had x, w to y, w. So notice I do short leg to long leg. So I have x, w to y, w. That's going to equal, and then if I look at this triangle, I do the short leg to the long leg. So yw to wz. Notice that these two means are the same. So we have this geometric mean type of proportion written. So if you cross multiplied and did your proportion cross products, you'd have yw squared equals the length of xw times the length of wz. And so yw will be the square root of those two multiplied together, which is called the geometric mean. And since these two are the lengths of the hypotenuse, the two segments, then the altitude is the length of the geometric mean of those two segments. Then there's another corollary that says if the altitude is drawn to the hypotenuse of a right triangle, then the length of a leg is equal to the geometric mean of the hypotenuse and the segment of the hypotenuse closest to that leg. So the length of yz will be the geometric mean of the entire hypotenuse and the part of the hypotenuse that's closest to that leg. So you take the length of this hypotenuse times the length of this, take the square root, and that's going to give you the length of this leg. So if the altitude, and then I do dot, 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 right triangle, can I do that? So it's the same thing that we've written here. Then the leg, length, it's supposed to be length of the leg. I'll just put leg length is equal to the geometric mean of the hypotenuse and the segment of the hypotenuse closest to that leg. So if we were to do this hypotenuse to the shorter leg, so let's write a proportion first so you can see how it works. So we have xz, no, xz, yeah. xz is to xy as, and then if you look at the small triangle, xy is the hypotenuse, right? So we're going to do xy to the shorter leg, which is xw. And can you see now that xy will equal the square root of those two multiplied together? So you would take this leg right here of the great big triangle is equal to the geometric mean of the entire hypotenuse plus the part of the hypotenuse that's closest to that leg. Yes.
Okay, so here, we're calling it the geometric mean, but isn't it kind of translating into the length of a different side?
No, the length of the side is the geometric mean of those two segments. So what the geometric mean is you just take their two lengths, multiply them together, take the square root, and that gives you the length of the missing side, or the side you're looking for. So I'm going to show you two examples and then we'll be done, but I have to turn the page. So if you're not done yet, you can borrow my notebook after. So leave some room for that. We have a triangle QST. That is right. We're going to draw an altitude to the hypotenuse. Call it R. The altitude we're going to call X. QR is 6 and RS is 8/3. So the first corollary says that the length of the altitude is equal to the geometric mean of the two segments of the hypotenuse. So we can just say that X equals the square root of 6 times 8/3, which equals the square root of 16, which is just 4. So X equals 4 in this particular example. And we'll do another one similar to the first. Y, W, Z. We'll draw the altitude. This is a 9, 12, 15 triangle, and we want to find the two segments of the hypotenuse. We'll call them C and D. So if we do, remember the leg, the second corollary says the length of the leg, 9. So 9 is equal to the geometric mean of the entire hypotenuse. So 15 times the side of segment of the hypotenuse is closest to that leg. So 15 times D. And then the other one would be 12 equals root 15 times C. So we can square both sides. 81 equals 15D. And then divide, and D equals 5 and 6/15, which is 2/5. This one will square both sides. 144 equals 15. C, divide 144 by 15. I think C equals, so 60, 90. 8, so 9, 20, 35, 9/15, which is 3/5. There we go. Okay. Sometimes I get a little confused about it. You know, it's good to use those. I always, if I'm like, what, get a little bit confused, I'll just go back to setting up proportions. Like we always do, like short leg to hypotenuse equals short leg to hypotenuse. So if it becomes a little too complicated in your head, it's okay. Like, just go back. It is an easier way to do some of the things, but sometimes easier ways aren't always easier if you can't remember them. Okay,